Let us study today data structures topic trees. We start with basic concept of trees. Let us go through its definition. A tree can be defined as collection of nodes. It has a starting point, that is starting at a root node. Here A is the root node. This A is the root node. So the definition reads, a tree can be defined as a collection of nodes where each node is a structure consisting of a value together with a list of nodes called child nodes with the constraints that no node is duplicated. So here this B, this C, these are all nodes. E, G, J, these are all nodes. The definition states that each node has child nodes. So A has B and C as the child nodes. The root of a tree. The root of a tree understandably is A. This is root. It means it from A begins this tree, and A has child B and C. B again has two childs D and E, and definition also states that no child is duplicated, that each of these A, B, C or G, J, these are called as nodes. These are all nodes. A, J, L, these are all nodes. They have values stored in them, and each has child nodes. Now have a look at this example. You can see what is an edge. The line joining two nodes A and B is called an edge. You can see an edge. This C and this H are example of nodes. Nodes are also called as elements. So this is a binary tree. The word binary means 2. So why binary tree? Because each node has maximum of 2 nodes. So binary tree has maximum of 2 nodes. Now we study the left subtree and the right subtree. In trees, context of trees, two words will be used regularly: subtrees, left subtree and right subtree. So you can see in this diagram this lining, this lining, this covering you are seeing here to the left of this A. This portion is called left subtree of A. Similarly, the right side of A, this portion covering elements C, G, H, J, K, L, this is right subtree, and this portion is the left subtree. Again, we repeat some of the basic concepts of tree. A is root node. You can see root node. This B, this is the left child of A, or it is also called as left successor of A. This C in the red color, you can see this is right child or the right successor of A. The nodes L, F and D are distinctly similar from other nodes in the sense that these are the nodes where the tree is ending. So these are called as leaf nodes. D, F and L. These are called. Similarly, G is also one of the leaf nodes. Now we studied levels in a tree. Visibly, we can see in this diagram these are levels. Now, these parallel lines you are seeing, these are different levels. So we have the topmost node as A. So the level comprising the topmost node is known as level 0. The two child nodes of A, B and C are at level 1. You can see this is level 1. The childs of B and C, the immediate childs of B and C are D, E, G and H. So these are considered to be at one level. So we start our numbering from 0, then 1, then 2. Similarly, at the last we get only one child node of a parent node J. J has child node L. So this is the last. This is called level 4. So we have 0, 1, 2, 3 and 4. Now we study the depth of a tree. The depth of a tree is also called as height of a tree. The depth or height of a tree is the number of levels is equal to the number of levels in a tree. Here you can see this tree has 5 different levels. So the depth of this tree is 5. 0, 1, 2, 3, 4. These are 5 different levels. Now we go to the textbook definition of a binary tree. We read out this text here. A binary tree is a data structure in which each node has at most 2 children, known as left and right. Nodes with child nodes are called parent nodes, and child nodes may contain references to the parent. Here the word reference means that parent node contains address of child. Address means the location. Now we study a complete binary tree. The definition of a complete binary tree reads as a complete binary tree or a perfect binary tree or a full binary tree. These three are the same structures, three names. So a complete binary tree is a tree in which all leaves are at the same depth or same level, and in which every parent has two child nodes except possibly the last. To understand exactly what a complete binary tree or a perfect binary tree is, we draw a diagram. Have a look at this diagram. This is a complete binary tree. The definition states that all the labels must be completely filled. So the label 1 can have maximum of 2 child nodes for A. So B and C are filled. Now label 2 can have maximum of 4. So D, E, G and H are filled. Similarly at level 3, L, M, F, N, O, P, J, K are filled. The rule states that if there are some nodes still left to be filled up in the tree, say RST, so we start from this side, from the left hand side. So the L must be filled with the left child node, then L must be supplied with the right child node, and that still if there are some more elements to be filled, so take M from the previous level and fill the left of M. This is the way in which you will fill a complete binary tree. Now I again present to you a binary tree which looks like a complete binary tree, but which is not a complete binary tree. Not. How? Level A has maximum of 2 child nodes B and C. B and C have both child nodes filled up. Maximum number of child nodes of a node is equal to 2 in complete binary tree. CBT means complete binary. So up to this level, this is a complete binary tree, but when we start to the next level, L has been supplied with left and right, but M has directly been supplied right child node, and the left child node has not been supplied with before T. So the left child node of M is empty and right node is present, therefore it is not a complete binary tree. Let us take one more example of a tree which is not a complete binary tree. See this tree. A has 2 child nodes B and C. Similarly, B has D and E has 2 child nodes. C has G and H has 2 child nodes. But in the next level, L and M has been supplied, F and N has been supplied to E, O and P have been supplied to J, but before supplying both elements of H, we have started a new level. So the previous level is empty and new level is present. So H has not been supplied with a child node, the right child node, and we have started filling up R, S and T at the next level. Therefore, this is not a complete binary tree. After having studied the example of a complete binary tree and those examples which are not a complete binary tree, we come to the conclusion of some rules. So we text down some rule here, we note down. Let us note some rules. Rule number 1. A node will have maximum of 2 child nodes. Rule number 2. A new node will not have child node until all previous nodes at the same level have two child nodes starting from the left. A new level will not start until previous level is full. A parent will have first left child node filled. If left child node is present, then only the right child node is filled. Now let us move to the numerical portion of binary trees. Let us start with a small topic that is calculating the depth of a complete binary tree. Depth of a complete binary tree. We denote a complete binary tree with the notation dn. Now you may be asked that if a tree has n nodes and it is complete binary tree, then what is the height of a tree, where n is a natural number, which is the total number of nodes in the tree. That is, n is either 1, 2, or say 8, 9, 127, 128, like that, any number. To calculate the complete binary tree's depth, we need to know a basic function of elementary mathematics called as floor function. The floor function fx is defined as the greatest integer that does not exceed x, and its notation is like this. Say we have a number 7.5, so we need to calculate the floor of 7.5. It is 7, because 7 is the greatest integer less than 7.5, because 8 is greater than 7.5. Similarly, minus 7.5, the floor of minus 7.5 is 8, because minus 7.5 is greater than minus 8. And if we go to minus 7, so minus 7 is greater than minus 7.5, so minus 7 is not the floor, minus 8 is the floor, because minus 8 is always less than minus 7. The floor of minus 20 is minus 20, because it can be less than or equal to. If I say the word does not exceed, it means less than or equal to. So minus 20 is the greatest integer that is less than or equal to 20 minus. We take an example now. If there are 8 nodes in a complete binary tree, then calculate the depth of the tree. Let us solve this question now. The formula is floor of log of total number of elements n to the base 2 plus 1, and we take floor of this. This is the formula for calculating the depth or the height of a binary tree, complete binary tree. We denote it with dn. So if there are 8 nodes, 8 to the base 2, we take the log, then add 1. 8 is 2 raised to the power 3. Now 2 raised to the power 3 can be written as 3 log 2 to the base 2. Again, log 2 to the base 2 is equal to 1. This portion is 1 from the identity that log n to the base n is always 1. So 3 into 1 is equal to 3. That is why this 3 has come. Then this plus 1. 3 plus 1 is equal to 4. This is the identity log n to the base n is equal to this. Now we take the floor of 4. The floor of 4 is equal to 4 because 4 is the greatest integer less than or equal to 4. So the depth of the tree is